Good morning. This time we will consider Schrodinger's equation. Remember that we have previously discussed quantum probability amplitude. We have discussed the state vector and we have considered the quantum mechanical operators also. We have considered how to construct the quantum probability amplitude out of superposition of several several waves of omega and k, where omega is a function of k and slowly varying in the region omega plus minus omega 0 plus minus delta omega. Similarly, k equals in the range of k0 plus minus delta k. Now, we know that if quantum mechanical probability amplitude is expressed in position coordinates or in r, then this is called wave function psi xt or psi rt. This wave function is constructed by this wave function is constructed by several waves of omega and k, and omega varying with k in a very small slow manner. Similarly, the wave packet that is constructed is such profile of amplitude of omega and k that this wave packet is confined in delta x around the mean position delta in the mean position x0 plus minus delta x interval, and it travels with velocity or signal velocity vg is equal to dx by dt, that is d omega by dk of the superposed waves, and this wave packet or this wave amplitude moves without distortion. This understanding of forces us to demand that the differential equation obeyed by quantum mechanical probability amplitude QPA must be linear in nature. First, why it should be linear? So that all the solutions, all independent solutions so that all independent solutions of the equation can be superposed. If it is not linear, then this would not be possible. Secondly, the coefficient of the equation must be such that it should be free from it should be free from it should be free from variables e, p, omega and k and angular momentum. These five things should not appear in the in your angular in your constant coefficients. That is what it means. So the coefficient of the equation that we want to study now should be independent of this, and it should be linear. Okay. Now, if we take the wave as e to psi xt wave function as e to the power iota within parenthesis kx minus omega t, and c is any constant, so c e to the power iota within the bracket kx minus omega t. This correspond to the particle of momentum p, where p is equal to h cross k, and energy E, where E is h cross omega as well as p square by 2m. I mean free particle. Then what happens? If I calculate d psi xt by dt, if I calculate d psi x by dt, then what happens? I get something like minus iota omega and psi back. If I multiply the whole thing by h cross, then h cross omega is E. Then what I get is that iota h cross d upon dt will give me E psi. That is the equation 4, that what we are saying. That means if I want to get E as the eigenvalue, then I should have an operator iota h cross d upon dt, right? D upon dt. That's what I should have, and that is that. Similarly, now let me calculate d2 psi by dx square of xt. Then I get iota k whole square multiplied by the wave function. And if I say h cross k is p, if I put, then I get this thing minus h cross square d2x upon dx square psi x wave function, p square, and this thing is this. Okay, now dividing it by 2m, and we say that it is minus h square upon 2m d2 upon dx square psi x will give me E psi xt. Now equating 4 and 6, because both of them are E psi and E psi, then I get that iota h d psi by dt is equal to E psi, or equals to minus h square upon 2m d2 by dx square psi x. This equation. This is the Schrodinger's equation in one dimension and free of any potential, because we have not added any potential so far. Similarly, here you can say in this Schrodinger equation format that iota h d psi by dt, d by dt, can be identified as an operator of energy E is taken as operator E, and minus iota h d by dx can be taken as operator for px, and minus iota h cross del vector can be taken as operator for momentum, total momentum, and minus h cross square upon 2m del square is taken as kinetic energy, that is p square upon 2m of the particle. So in the case of a free particle, it is the total energy. So referring back to our previous discussion of linear operators of quantum mechanics, this we can write that energy of a particle E can be written classically as p square upon 2m plus potential. Similarly, if we put the operators corresponding to that, we get that corresponding to E, iota h d psi by dt, and p square upon 2m we write minus h square del square upon 2m psi, and v corresponding to v we have v operator. Then for a particle of energy, total energy E, momentum P, which is moving under the influence of potential V, we can write the Schrodinger's equation as iota hd upon dt of psi equals to minus of h square upon 2m del square psi and VRT of psi. This is the time dependent Schrodinger equation, and if you don't write proportional Schrodinger's equation time dependent, then you can simply write minus h square del square 2m psi V psi equals to E psi, where E is the constant of energy and it is E. So that means if we represent wave function SIXT, and which is made of, this is quantum probability amplitude made out of superposition of several waves and following the Heisenberg's uncertainty principle and moving with the velocity of v of the particle without distortion, then this follows quantum mechanical equation where the operator iota h d by dt is energy operator, minus h square upon 2m del square plus v is the Hamiltonian, that is the energy operator time in the space part, and therefore we get this equation that iota h d by dt psi equals to h psi equals to E psi. That is the Schrodinger's equation in general. And that is the end of our chapter today, our discussion. Thank you.